look at 11.2, which is another continuation of chi-squared. But we're going to take a look at two other different types of chi-squared tests. The first one that we're going to focus on is going to basically take a look at a single categorical variable across several populations. So we're going to take a look at a distribution of categorical variables like the goodness of fit, but we're going to compare it from different populations or sometimes different treatments. Okay? So in order to do something like this, what we want to actually have to do is we have to start to look at their conditional distributions, because you're going to have to take a look at it, okay, from each and every population and then look at those results and see, is there statistical difference? Or is there something statistically going on that would cause you to think one population is better than other when dealing, with whatever the categorical variable is. So what we do is we kind of walk you through a problem slowly but surely, kind of analyzing it first, and then we'll piece together how you do the test. So to start us off, this first example here, it says, whoa, I didn't mean to jump like that, I apologize. It says, an article in the Journal of American Medical Association reports the results of a study designed to see if the herb St. John's wort is effective in treating moderately severe cases of depression. The study involved 338 subjects who were being treated for major depression. The subjects were randomly assigned to receive one of three treatments, St. John's wort, Zoloft, or placebo for 8-week period. The table below summarizes the results of the experiment. So you can see here's the one category that we're looking at, either full response, partial response, no response. The populations are St. John's wort, Zoloft, and the placebo. You can think these are each one treatments, and we're taking a look at how many people responded to each of these. Okay, and so we want to see, is St. John's wort different than that of Zoloft? Is it different of that than the placebo, or vice versa? So we're going to compare them all at one time. So the first thing we want to actually do is calculate out the conditional distributions in proportions of the type of response for each treatment. It's not good to compare the actual numbers, because you might be saying, oh, look at this, placebo had the highest number of full responses, but they also had more people in their group. So you need to change them to proportions. So you're looking at what proportions of success in each group did they have. Okay? So down below here, I took a minute and calculated out the conditional distribution in proportions. So with St. John's, notice here I'm dividing by 113, so 27 out of 113, 16 out of 113, 70 out of 113. Did the same thing here with the Zoloft, did the same thing here for the placebo. So now you can start to compare them by proportions, and now what you want to basically do is take a look at these proportions and see, boy, does it look like one treatment is more effective than the other. So one of the ways that we can do it is by making an appropriate graph. So here what I've done is I've done a side-by-side bar, or I apologize, a segmented bar graph. You could do a side-by-side bar graph also. So as you can see in purple, full response, and kind of this light tan brown was partial response, and no response, okay, was in hot pink here. So what you can start to see here, okay, if you were to combine like full and partial response, Zoloft seems to be the best, followed by actually the placebo, then St. John's wort. But if you're just looking for full response, the placebo is actually the better, then Zoloft, then St. John's. So the question starts to become, okay, what's going on here? Okay? So down here in the bottom, we basically talk about it here, about what's going on. So overall, Zoloft had the highest proportion of at least some sort of response, as I mentioned below, okay, followed by the placebo, then St. John's wort. But the biggest surprise I found was that the placebo had the highest proportion of subjects with full responses. Now that makes you kind of wonder sometimes about Zoloft. Now again, this is just one sample data, okay, from the from the Journal of American Medicine Association. Okay, but Zoloft is a prescription that's given to some people to help with depression. right, so now, how do we go about doing a test here? Right, so if we go to the next page, it says, notice how in the previous problem you're trying to compare from 3 different populations or treatments. In order to see if our results are statistically significant, you have to write this null and alternative hypothesis. So your null hypothesis will basically say, okay, there is no difference in the distribution of categorical variable for several populations, while the alternative is, hey, do we have a difference? So for our examples, our null and alternative hypothesis would look something like this. There's no difference in the distribution of responses for patients with depression when taking St. John's wort, Zoloft, and the placebo. While the alternative is going to say there is a difference in the distribution of responses for patients with depression when taking St. John's wort, Zoloft, or a placebo. We started to see a difference. The question is it statistically significant? Does it make you go, something's going on here? Okay. All right, so the next thing that we need to actually do in the problem is to calculate out the expected counts. This is where it becomes a lot of fun, and it actually requires us to do a little bit of work. Okay? So to calculate out the expected accounts, we can use this particular formula. Okay? So the formula is this. An expected count is simply the row total times the column total divided by the table total. Okay? So basically I'm going to kind of show you why this formula works the way it does. If I'm trying to figure out the expected count, okay, for St. John's wort, okay, with having a full response, you kind of look at it this way. Okay? First of all, what we would expect to happen here is we would basically be looking at it as independent events. What we would do is we take a look at the probability of St. John's wort and full response should equal the probability of having someone with St. John's wort times the probability of them having a full response. So if I look at this, okay, the probability of picking someone with St. John's wort is 113 out of 338. Times the probability of them having a full response, there's 91 full responses out of 338. Now the reason why I'm saying this works again is because it's independent. That's one of the conditions. Okay? Now this is a probability, but I want an actual count, so I have to multiply by 338. So what happens is one sets of the 338s cancel out, and you'll start to see row total times column total. I apologize, I flipped those around. This would be row total times column total divided by table total. Notice how those numbers are matching up right there. So this is a quick way of doing it, but this is why it works the way it does. So what I've done down here, you'll probably want to pause the video to get them, but I've done them all. Okay? So we saw 27, we expected 30.4. So 113 times 55 divided by 338 gives me 18.4. That's what I did here. I expected 16. So to compare this 70 here, 113 times 192 divided by 338. Do the same thing for Zoloft. Now it's 91 times 109 and 55 times 109 divided by 338. I apologize, but you're hopefully seeing the pattern. So I get the expected counts for all of them. So here's all my expected counts. Here are all my observed accounts. Now the question is, how much do they differ by? Okay? So on the next page is, we want to calculate out this p-value. So now with the p-value, we have this new concept called, or we still have the old concept of degrees of freedom, but how we calculate it out is differently. To calculate out your degrees of freedom, you take how many rows and how many columns you have, subtract one from each, multiply them together, and you get your degrees of freedom. Okay? If you're wondering why it works the way it does for this, please stop me in class someday and I'll show you why it works the way it does. Okay? I'm just going to keep it as that, otherwise this video will probably get pretty long. So in our particular case, our degrees of freedom, 3 minus 1, 3 minus 1 because we had 3 responses, 3 types of treatments, 3 minus 1 is 2, 3 minus 1 is 2, 2 times 2, our degrees of freedom is 4. So now what you can start to see down here is I'm starting to calculate out my chi-squared statistic. There's technically 9 of them. When they get this big, what I tell students is write out the first one and write out maybe the first 2, and then you can go dot, 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 and write the last one, okay? Now, when I go to calculate this, I like to use my calculator to help me out a little bit, because trying to do each and every single one of these one at a time can be a pain. So, one of the things I do is I use my calculator. I enter all my observed values in list 1, all my expected values in the list 2. They have to be in the same order so they match up. And then I do observed minus expected, because that's what L1 and L2 are, squared divided by expected. In my list 3, I actually have them do the calculations of each and every one of them. And then what I can do is go one variable statistics, and to get the sum, my chi-squared statistic, I'm just doing the sum of x, okay? So to show you how to do that, I'll pull up my calculator here, and I'm actually going to have to jump back to the previous page, okay? So one of the things that I actually have to do is go to my table here. So I'm going to this table right here, and I'm going to enter in all my data, and I'm going to do it column by column by column, so I have to match them up right here. So in my calculator, if I go to stat and I go to edit, I have some data in here, so I'm just going to clear it out. So I'm going to start typing these in. So hopefully I do this right. 27 and 16 and 70. So this is going to take a little time, but it'll probably be worth it. 27, 26, hopefully you're following along, 56, and I do the last column, 37, 13, and 66. Okay, so these are all my observed values, that top table. Now these are all my expected counts in the same order, so I gotta go column by column. If you don't, then you're messing up and you're gonna get a totally different chi-squared statistic, 64.2, and then 29.3, and 17.7, and 61.9, and 31.2, and 18.9, and 65.9. So, alright, so now I have those in here. So what I can do is go over to list 3, make sure your cursor's on L3, and then I can go ahead and then type in my observed minus expected squared. So what I'm going to do is in parentheses, list 1, second one, you can see how it pops up there, L1 minus second 2, L2 parentheses, squared divided by list 2, so second 2. Hit enter, and it calculates out each individual chi-squared statistic. And I apologize that I didn't talk about this before, but this is kind of neat to have these values, because then you can start to see which one is contributing the most. So right now you can kind of see here that this one right here, expected 26, got 17.7. That's one that's contributing probably the most difference between them. So, as I mentioned before, I'm going to go stat, calculate, one variable statistics on list 3, because I want to get the chi-squared statistic. Look at the sum of x right here, okay, 8.77. So then what I can do is I can go, all right, chi-squared, so second bars, number 8, chi-squared CDF, 8.77, comma 999, comma my degrees of freedom was 4, and that's going to give me my p-value, 0.067. So let's see how Mr. Bartz actually did. I'm hoping he did okay. 0.067, how about that? So there's his chi-squared statistic, got the same value, my p-value. So then what I can do is make my conclusion. So our result, or one more extreme, would occur about 6.7% of the time. If the null hypothesis was true, meaning there was no difference between the 3 different treatments. Our p-value is greater than 5%. Okay? So we do not have statistical evidence that there is a difference in the distributions. Even though this was a low percent, it wasn't significant enough to say that there's different responses to depression when taking St. John's wort, Zoloft, or the placebo, which is kind of a bummer for Zoloft, but at least here in this study we're looking to see if St. John's wort is effective. So in a nutshell, that's basically how a goodness of fit test here, I apologize, it's not a goodness of fit test. What we actually call this, I apologize, is we call it a chi-squared test for homogeneity, meaning there is no differences within the populations. Okay? So in the 4-step process, you'll state there is no difference versus there is a difference. The chi-squared test is called a chi-squared test for homogeneity. Okay? The conditions are exactly the same as the goodness of fit test. Notice how all our expected counts were greater than 5, which was good. Independent, no problem. Simple random sample. We calculate out the p-value. The key part here is we have to do the expected counts. Okay? And our degrees of freedom does change. Okay? So we have a slightly different degrees of freedom. Okay? So I know I've been going pretty fast here. I do want to do one more example with you for a chi-squared test for homogeneity here. So let's take a look at our next example here. And it kind of goes back to chapter 1 with superpower preferences. So one of the examples that we did was we took a random sample of 200 children ages 9 through 17 from the United Kingdom who filled out a census at school survey, did the same thing with Americans, and we went with 215, and we wanted to find out, so here's their results. So we want to see if there's actually a difference between the countries and superpower preferences. So first thing we're going to do is actually calculate out, okay, the conditional distributions and a graph and see what's going on. So what I've done here off to the side here is I've calculated out their conditional distributions of each country, UK in red, US in blue, and I've graphed them. So the question is it statistically different? You can start to see some of them are similar, you know, super strength and visibility seem pretty close, but boy, telepathy seems to be a lot more US students, but flying definitely higher for UK. The question is it statistically significant? Okay? So to go through the test, you're going to have to write small here, but our null and alternative hypothesis would say there is no difference in the distribution of superpower preferences between the 2 countries, UK and United States. The alternative is to say there actually is a difference. So you may want to pause. So I'm going to keep going here. So now, our plan, I'm going to say we're going to do a chi-squared test for homogeneity at the 5% significance level. So, is it random? Yes, they took two simple random samples, 200 UK students, 250 US students. Large sample sizes, all expected counts are greater than 5. So over here, I went back to these proportions, okay, and calculated out the actual counts that I would expect. So I went back to the table and went 200 times 99 divided by 415 to get the expected count for flying for UK. So I did all of that already ahead of time to get all these expected counts. That would actually take you a little bit of time to do. But once I have all my expected counts, I can see that they're all greater than or equal to 5. Likewise, then independent, they are both independently sampled, so UK students shouldn't influence a US superpower preference and vice versa. And then make sure the population is greater than 10 times the sample. So in this case, there is at least 2,000 UK children and 2,115 US children. So now, calculate out the chi-squared statistic. Okay? So, I would do the first one, okay? And then the second one. And then I'd go dot, 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 and the last one. But I'd use my calculator, list 1, list 2, and list 3, enter in the data in order. I get a chi-squared statistic of 6.29. My degrees of freedom here, I had 2 columns, 5 rows, 1, 2, 3, 4, 5. So 1 times 4, degrees of freedom have to be 4. So I can calculate out that p-value, chi-squared CDF 6.29 to infinity, 4, gives me a p-value of 0.179. So in this particular case, that would tell us we would not be rejecting, meaning our sampling distribution, the one that we got, or one more extreme, would occur 17.9% of the time if the null hypothesis was true. P-value is greater than 5%, so we're going to fail to reject the null hypothesis, meaning we do not have statistical evidence that there's a difference in superpower preferences between UK and US children. All right, so this ends at least part 1 of the 11-2 notes. You'll watch the other video to get the second part of it. All right, and that is good.